So last time we talked about sets, and I'm jumping back to dictionaries. So dictionaries are an absolutely amazing data structure for many reasons. The beauty of how they're so good is something like what makes them so good and like why they're so good is a topic that's outside the scope of this course. It requires quite a bit of understanding of some concepts before we could really get into it, but we could still get a high-level idea of how it works. But even how we use them is phenomenal. It's fantastic, it's great. So a lot of their complexity is hidden from us, for better or worse. Now, simply, it's like a list, but like with a list, we index it with numbers. 0, 1, 2, 3, whatever. And there's like an orderedness to the numbers, right? Because of like what's after index 0? Index 1, right? But unlike lists, dictionaries can be indexed with things like strings. You can index a list with a string, which is kind of a weird idea. And they don't have to be strings. You can index the list with anything that, like a lot of different types of data. But you can index dictionaries with strings. So consider the following little example, right? This example creates a dictionary. It starts as an empty dictionary. That's what's happening on line 2. Then we are adding 3 records to that dictionary. The first one is at index Billy. The next one is at index Sally, and then we have Jimmy Bob. And they are each having assigned a value. Now in this particular example, the strings that we're using to index, not in this example, like in general, the thing we're using to index, like here the strings Billy, Sally, and Jimmy Bob, that's what we call the key. And the key must be unique. And the value associated with the key is called the value. That's it. No magic there. It's just the value. The values don't need to be unique. In the same way, you can think about a list too, right? There's only one index 0. And it might have the value x in it. There might be another value x in that list, but there can never be another index 0. There's only one index 0. They're unique. So the keys must be unique. And then if I were to print out this dictionary, this is how it would get rendered for me. Billy, 44. Sally, 88. Jimmy Bob, 99. There technically is no ordering associated with this collection, this thing called the dictionary. But sometimes Python makes it seem like there is. So in this above example, a dictionary was created, and we added 3 values to the dictionary. This is an example where I started with an empty dictionary. I can make a dictionary. No. I can make a dictionary kind of with this syntax to, here, I'll show you. Here I'm not starting with an empty dictionary. I'm creating the dictionary with those values in it in the same way that I can start with an empty list. Right, like I can go like this and then append to it, or I can say A is 955, oops. Right, like in the same way. So here I'm making a dictionary. Now let's start with an empty dictionary. For this example, what should be the first key? Give me something.
Hot sauce.
Hot sauce. That's what you said, right?
Yep.
Perfect. And what value is associated with it? Letter. Cool. Give me another key. And what should the value be?
Value.
Cool. Give me another key.
Value.
Let me guess. Oh, okay. Yeah, fair enough. Yeah, you're right. You're foolish. And let's do one more. How about let's do the tuple 99 and 4. And that, of course, is 1, 2, 3. And then if I go down here and I print it out, there we go. Cool. The string hot sauce, the key, is associated with the value letter. Then the key is associated with the value. The key value is associated with the value. And then the key, the tuple 99 and 4, is associated with 1, 2, 3. Now, one thing you might come across is if you're like, oh, so I can actually use like anything as a key? Yeah, well, let's see what happens. Dictionary. Let's give it the list like 0, 1, 2, 3. That's fun. And its value is good stuff, but that won't work. In fact, you see this funny little word at the bottom that says unhashable type. So this then begs the question, what on earth is, what's hashable? What does that mean? Well, we'll talk about that later. So some types won't work as a key. You can use integers as a key. Oh, wait. Let me just go here and do. Like 99 works as a key too, but it's important to note that this is not a list, it's a dictionary. Okay? One time I had a friend use a dictionary, and all their keys, they used the integers 1 through n, which was just a goddamn nightmare for hopefully obvious reasons. But you could do that. So here we go. And so you might ask, well, how do I access? Like, how do I get? Like, if this is how I assign a value at a specific key, how do I get a value at a key? Well, that's, well, here, let's do hot sauce. We can just index the dictionary at the key, and it tells you it's hot sauce. And then you said, well, okay, they have to be unique, right? So they have to be unique. Well, let's test that. Do they really have to be unique? Well, what if I want to make a new hot sauce? It seems to have worked, but of course, if we go print out the whole dictionary, we actually overwrote what was at that key. So like we can't add a duplicate key because that would just mean we're overwriting it. So it's, yeah.
Why does it override the bottom one? Why doesn't the top one take that? Line 12, why is that the one that pops up, not the one on line 3?
Like here? Well, it was set to, imagine I created a box. It's like creating a variable, really. It's like imagine I made, let me grab a marker first. The answer is probably simpler than you think. It's because I have this dictionary represented as a blob, and in that blob I have a box, and in that box is labeled hot sauce, and in there I have letter. And then I have another box called key. And then I say, okay, go make another box called value. And so on and so on and so on. And then we get down to line 12 and we say, okay, go to dictionary at hot sauce. Oh, that already exists, so we're just going to like overwrite this. So the original one is like obliterated like a variable being overwritten. So that's why, like, well, why didn't we see the first one? Well, because we obliterated what it was and replaced it with something else. There, now it's true. So why don't we see it? Well, it was letter, and let me make it more obvious, maybe by doing this. The first time it's printed out, it's letter. Then we overwrite it, and then we print it out again, and we can see, okay, yeah, it's changed. Does that answer your question? Awesome. You have a question?
Can the key be a list?
I already showed you. And the answer was, what did?
Well, in the dictionary,
Oh, the value. The value absolutely can be a list, yes. And let's do a quick example of that. Let's make hot sauce the list. Actually, yeah, let's make it the list of 5, 2, and the dictionary. Oh my, no, oh my. Nope. There, it's all there. It's all good. Yeah.
I assume the key can't be a pointer to a list either, right?
It can't be, well, it wouldn't, but by trying to make it a, okay, let's, when I made that list, so it's interesting. When you make a list and you're like, well, you made the list. When you make the list, that statement actually like gives you the pointer. So yeah, it's the same thing, but let's just show you A equals. Yeah, it's not going to work. But if I were to say, turn this into a tuple, how do I do that? There. Well, then it's fine. Because a tuple is hashable, but a list is not hashable. What is hashable? That's weird. What is that? And more questions about this example? Any questions or anything? Yes?
Instead of it like going just sideways, can you make it go down?
What do you mean?
Like the list stuff?
You mean in how it's printed out?
Yeah.
Well, of course you could. All you have to do is go like, okay, fourth thing in my... We can iterate over dictionaries. We can kind of like make it go like this. But you'll notice it actually only ever prints out the keys. So we would actually have to say like my dictionary at thing. There.
What about with like the keys next to like the values?
Well, this is hot sauce letter. I mean, we can. This is all just how we're parsing it, right? There's no, it's just how I wrote the code to make it printed out like this. But there is like when I print out a dictionary, I get what I get. I get it like this because that's what happens when you print out a dictionary. We will learn, how does Python know how to print out a dictionary? We'll learn that pretty soon, actually. Does that answer your question, though? You would just have to write the code to do it the way you want it to parse. Or not parse, be like, what's the word I'm looking for? Displayed, I guess, yeah. All right, so in this example, the dictionary ability, blah, 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 blah. Okay, cool. And updating, well, that's, okay. So why they're great? Well, imagine that this was solving the problem for me of, let's pretend for a moment, forget everything you know about dictionaries, throw it away, okay? So I say, I want to have some data in my computer where I'm storing each student's grade, okay? So what I could do is I could store that data like in a list, or a tuple, doesn't really matter, but I could store that data in a list. So what I'll do is I'll create this thing here called my grade, started as an empty list, and then go in and add each student's name and grade, name and grade, name and grade, and I print it out and I get this. That's great and all, right? Right? This shouldn't scare you. This should be relatively straightforward at this stage of the semester. But if there is a question, ask now before I carry on, after I preface it with, of course you have no questions. But for real, if you have a question about what you see here, ask, because if this doesn't make sense, the next part ain't going to make sense. Realistically, by the way, if I had this, like can anyone tell me why I might not want this to be a double? Or sorry, why I might not want this to be a tuple? If you don't, I won't be surprised if you don't have an answer, but someone in here might have an idea. Yeah? Yeah. Yeah, and I mean, if we're using this as a general purpose data structure, grades change. A tuple's immutable. I mean, there's a workaround where I replace the whole tuple, like replace the whole index of that list to be a new tuple with the name and the new grade. I could do that, but you know. So, yeah?
Tuples also have like no methods.
Yeah, they have no, that's true. Maybe some of the built-in methods could be handy too. But yeah, I mean, you put that together, that's a perfectly good reason to not use a tuple, yeah. So there we go. So if I were to say, so this is obviously a class with 3 students in it, but let's say I had a class of 300 students. And I add it all, it's great there. And I go, okay, great. I want to, like, okay, what was student Stephanie's grade again? Well, I would have to do some sort of like linear search, right? So here we go, linear search, my grades for Sally. So imagine I have this linear search algorithm. I would have to go through that list. Here, let's write it so it's clear. All right, there we go. And person. Now, based on how I know I've encoded the data, I always know that index 0 of the lists inside the bigger list. Index 0 is always the student's name, right? So what I'm going to do is say for record in grades, if person is equal to record at index 0, right? Because grades will be like this list of lists, right? So the first time through the loop, record will be the list Billy, comma, 74. The next time through the list, it's Sally, comma, 88. Yeah? So I say, is the person I'm looking for equal to the record at index 0? Well, that would be Billy, Sally, Jimmy, Bob, and so on. Right? Yeah? Good. So if it is, return record at index 1. And if I ever get to the end, they weren't found, we'll have like a sentinel value of -1, right? So then I can go and say print linear search grades, my grades, no. And we'll look for Sally. And we get 88. And now let's look for Cassie. Well, there's no one there, right? Whatever. This is just a linear search. It's a little fancy because we had to index certain things with each record in the big list. But it's just a linear search. That's it. Nothing special about this. Before I carry on, do we have any questions? Yeah.
Could you put like an input into that to like input the person's name?
Yeah, we could. But I mean, what I would do, so this is a design thing I'm about to show. I would only, like, I wouldn't want to write an input inside a function. I would want to leave things like input, output outside, like at the top level of your like program. And when I say top level, what I mean is like basically the most unindented thing. Because you can have functions calling functions, calling functions, calling functions. I don't really want to be doing I/O in any function. I want to be doing it at like the top level. It's a little better that way. But yes, we could. Oh, I thought I saw another hand. Was there another hand? No? We're good? Okay. So a linear search. Now, as we've talked about several times, with linear search, if I have 3 records, worst case scenario, how many things do I got to look at to find the thing I'm looking for? Or not find it, for that matter. 3. What if it's 300? What if it's 3 billion? Yeah, it's a linear search. There's nothing special about this. Now, okay, look, we've got this. We had a list of lists. That's great. It's effectively storing like the same data as that dictionary was. Now you can remember what I told you about dictionaries, right? You can bring that back into your mind. This is storing like the same thing as the dictionary. But with the dictionary, I wouldn't actually have to do a linear search. Like, I had to write the linear search for this. With the dictionary, I could just say, okay, get like index the dictionary at the key where the key is the student. Now, realistically, in a case where you wanted unique values for keys, you wouldn't use a first name as a key. That's a terrible idea. You would use something like a student number, for example, because that is unique. But for our purposes, this is fine. So here, this eliminates the need to write a linear search. Isn't that nice? I don't need to write the linear search. I just say, hey, I'm indexing the thing Sally, and it gives me back the result. It just gives it to me. I didn't need to write the linear search. Before, with just the lists, I had to write the linear search to get Sally's. I had to call an extra function to do it. Then you're going to say to me, well, okay, I know you didn't write the linear search, but I know enough about programming now that even though I didn't have to write it, somebody else did, and it's just calling a function that's built in. You're wrong. Dictionaries are somehow magical. This is an exception to that rule of like, well, if I write the in operator, I don't actually have to write the linear search. Well, no, but somebody did. If I'm using a dictionary, I didn't need to write the linear search. You're right, and nobody had to. There's no linear search involved here. Well, at least not in the way you might think. A dictionary works quite differently. So, like I was saying, remember how the sum function still required the computer to look at each value in the list, but that functionality was hidden from us. Dictionaries are not simply hiding the linear search from us. Its actual underlying functionality does not need to do a linear search, although there are some exceptions to this. We will not be going over the details, but you know what? Because I know you're itching to know just a little bit of like, well, how the hell does it really work? Raise your hand if you kind of want a hint. Of course you do. So here's the magic. Remember that word, unhashable? Hashable. What's that mean? Unhashable, hashable. Here's the idea. And I'm going to warn you, I'm going to keep this at a high level. I am not going to go into more detail. It's outside the scope of this course. I don't want to distract you with things that could be overly distracting. We have a magic. Here's what we do. I want to create a dictionary. Here's what the computer's going to do under the hood. The computer's going to go like, oh, you want to make an empty dictionary? I'm going to go set aside this giant chunk of RAM over here. We could think of it as a list with indices 0, I'll just show kind of like some sections. And so on. 0 through, I don't know, n, where n is some arbitrarily large value. So we could think of setting aside a chunk of RAM as just like a list, okay? 0, 1, 2, and so on. So far, so good? I've created an empty list, but the computer has gone and set aside a giant chunk of RAM for us. The next step is we have this magical function called a hash function. And the computer scientists fantasize about this thing called this perfect hash function that doesn't exist, but we dream about it. So it's this very fancy function called a hash function, h, of x. It's a function that takes something that must be hashable. A list is not hashable. A string is hashable. An integer is hashable. A Boolean is hashable. A lot of things are hashable. A tuple is hashable. We need this magic function that can turn, all it does is it takes some input, something that's hashable, and it turns it into a number. That's all it's doing. It turns it into some number. Okay? So when I give, and then we make sure that number that we get is between 0 and n, okay? So when I give h, the function h, the string Sally, it goes, that's number 314. And we put in Sally, what did Sally have, 74 or something? 74. It goes there. Then it goes Jimmy Bob. Okay, when I put Jimmy Bob in the hash function, it goes, oh, that's obviously 1. Jimmy Bob had 99. He's crushing it. And then we throw another thing into this, and it gives me another number. And it'll, I don't know, and we go down into here, which is like 574. And here we have 42, and so on, and so on, and so on, and so on, and so on. Now, the hash function is deterministic, meaning when I go back and be like, what was Jimmy Bob? It says, well, it was 1. What was it again? It's 1. It always gives me the same thing for whatever the input is. But the hash function ideally takes some input, and it'll give you a unique integer. Then, when I come along and say, what was Jimmy Bob's grade? I just pop it into the hash function. It tells me it's 1. It didn't need to do any long computation. It just, the hash function, I don't know what it could be. It could be like the length of the strings. I don't know. It could be anything. I don't care. It's calculated like that. Jimmy Bob, it's 1. And it goes, oh, okay, well, it was 99. I didn't need to go look. I didn't need to go, are you Jimmy Bob, Jimmy Bob, Jimmy Bob, Jimmy Bob? I didn't need to do that. I just pop it in this function. The function tells me where to find it if it exists. Now, the downside of this is there's going to be a hell of a lot of wasted space. The upside of this is I don't need to go searching for anything. Now, you remember last time I talked about sets. And sets have this similar thing about like searching for things in them is like that. You don't need to do a linear search. And it's because sets are built off, presumably if it's what we have called like a hash set, sets are built off the same idea. But instead of storing a key value, it's basically, you could think of it as a dictionary where basically either something exists there or not, like a true or a false. Now, you might be wondering, well, what's that magic hash function? That's the kicker. There's a ways we do it, but there's no such thing as a perfect hash. And then you get things that we call hash collisions, and you have to deal with it. It's a whole thing. We're not going to get into it. But that's how it's doing it, is we have this magic extra function that we use that will map some input to a unique value, even though it will never actually be unique. It's not possible. But we hope that it is. So that's how dictionaries are so good. They waste space, but we can look things up like instantly. When I say instantly too, like what I mean is the amount of work that the algorithm, the amount of work the code has to do to go check if Jimmy Bob's grade exists and what is it, does not depend on the size of the dictionary. Where a linear search, it does. And as the list gets bigger for a linear search, the work goes up too. The dictionary can be doubled in size. It's the same amount of work, which is nice. Let's not go too far down this because it's outside the scope of this course. It's outside the scope of next semester too. This is like at least second year stuff. But that's to give you an idea of like where the magic is. That's where the magic is. It's really not overly complex. It's actually a relatively simple idea. But if you don't know it though, it seems like, whoa. But it's pretty cool stuff. Sets, yeah. There we go, cool. Any last questions before we move on to debugging? Anyone here have to debug anything before? Put your damn hand up. Of course you have. It's mostly what you do when you're writing code. Writing code, no one writes code. They just debug with brief periods of not having an error, right? Like that's what coding is, right? Most of the time you're debugging. Now, okay, you're writing your tests, but at this stage you're going to have had a lot of bugs and a lot of different types of bugs. By this stage of the semester, you've had a lot of experience with bugs. This is normal. And when I say normal, I can't stress enough where I'm like, you would be in the Guinness Book of World Records if you made it like a week through this course without having spent most of your time debugging, right? Like that doesn't happen. Like when I'm saying, don't be discouraged when you get bugs, like I can't stress how much where it's like, that's just what programming is debugging, okay? Programming, in their mind, like I've shown you before, everyone thinks programming is that I'm hacking away. No, that's not how it works. You write like one line at a time, then you spend a week wondering what's wrong with that one line. Like that's programming. All right, so it would be weird if you didn't have bugs. Remember, your code will be wrong every time you hit run until it's correct. That's another thing too, is it only needs to be correct once until you move on. It's going to be incorrect a hell of a lot of times until it's correct. You've probably come up with some systematic strategies that you follow to debug your code. And in this topic, we're going to talk about a few popular ones that are accessible and like you've probably been doing these things one way or another. And we're just going to take a moment to talk about them. And what I think happens a lot for programmers is they all know how they could more systematically find their bugs. But we have this aversion to doing it, where you're like, I don't need to resort to that, I could figure it out. And then 4 hours goes by, and then it's like, well, if you just goddamn did what you should have did in the first place, we wouldn't be here. Like, I hate to say it. Like, you're not that good, okay? Nobody is. And I'm not saying that you're not that, nobody is. You're not gonna like outsmart the system. Programming's out to get you. It wants you to fail, I think, right? So you got to have a good strategy for dealing with it. So there are a couple of ways to go about doing it. Now first, it's important to be aware of the different types of bugs we get. Some of the bugs we get are rather straightforward to solve, so much so that Python will even be like, you got a mistake right here. It tells you, on line 7, what the hell's that variable? And you're like, oh, I mistyped or something, right? Like there's a lot of those types of bugs. So, okay, remember that in this topic, before getting started, however, it's important to emphasize what this is all about. It's not just about getting your program to work. This is a key thing. It's about understanding your program and understanding why it's behaving the way it is. Far too often, especially since the introduction of those assert tests, do I see students go, here's my code, run, it didn't work. Let me change this, run, it didn't work. Let me change this, run, it didn't work. Slow down. The tests help tell you what was wrong. So look at what was wrong, look at your code, understand why it's doing what it's doing, and then fix it. Just hammering away and hitting run until it works, that doesn't make sense. Like that ain't going to work on the test. You don't have an interpreter on the test. All right, so the importance of debugging. As our programs get more and more complex, the types of errors we come across can increase in complexity. We have a lot of strategies that we follow, many of which I've been emphasizing throughout the semester, and how we even write our code in the first place to prevent a lot of bugs from coming up later. So that's an important thing to be remembering, is like you kind of hedge against the bugs and being a very defensive programmer. But no matter how good you are, you're going to be spending most of your time debugging. Beyond the obvious benefit of fixing your code, debugging helps us improve many important skills, like knowledge of your algorithms, knowledge of the programming language, the ability to reason logically, and the ability to reason about the flow and the execution of your code. Now, in many cases, often Python will generate an error message that will tell you what went wrong. Invalid syntax, right here. It even has a little up arrow pointing exactly where the issue is. And at this stage, you should be able to look at that code and go, well, yeah, I know what's wrong. So Python can be helpful when you've got errors like this. But sometimes you get errors that are a little bit more cryptic, Like you may, like that one that was like unhashable type. What the hell's that? I mean, I told you, but don't worry, when you get an error message that doesn't make any sense, you just throw it into Google and there you go. In fact, I think if you go, well, whatever, never mind. In some IDEs, if you even right-click, it'll be like, do you want me to Google it for you? Like it'll even like, it's built in the fact that you're going to want to Google this if you don't know what it is. Here we have it just because it's Chrome, and if I right-click, it says, you know, search for Google. Anyways. Common error messages that you're going to see and that you almost certainly have seen are things like syntax errors, indentation errors, name errors, type errors, index errors. These are all common errors. Now, actually, a funny thing is error is kind of a bit of a misnomer in this context, but we won't learn about that more until next semester. Syntax errors will cause error messages that are often helpful. Because the syntax, like Python knows what the syntax is supposed to look like. Python knows what your syntax looks like because you gave it to it. And it'll show you like, like it'll kind of try to be helpful in what's going on. So the message typically tell you where the error is, as seen in the above example. And yeah, okay. There's not much debugging strategy here. You just kind of do what it tells you. So how many bugs, how many errors do you see in this code? Take a moment, look at it, and count them. You got, yeah? Raise your hand if you don't answer it yet. Don't yell it out. Raise your hand if you have an answer in your head locked in. Okay, let's see. Let's try to run it and see what happens. Nope. It was never closed. What do you mean? Oh, it's backwards. Okay, that's 1. So who's going to be my counter? Okay, 1. Okay, I fixed it. 2, invalid syntax. What is that? You know what? I think it's probably this. It's probably that. That's probably what it. You have a question or you're just counting? You're counting for me? Cool. Yeah, that fixed. Oh, expected a colon. That's right. I forgot my colon. That's 3. What's the? Oh, I can't add the multiplication. Yeah, you're right. That doesn't make any sense. Let's assume I was just I fat fingered that one or something. And then what's this? Broken. It's not defined. What are you talking about? It says, oh, Borken. Broken. There we go. Okay, let's fix that. And then, oh, what's walrus is not defined. Oh, yeah, what's walrus? Jeez. Hey, we did it. How many was that? 6. All right. Some of them were syntax errors. Some of them were just like things were not defined. So, yeah, there we go. And we saw some examples where the error message was goddamn helpful, where it was like, you missed your colon. And then there are other cases where it was pretty helpful but less direct, where it's like, you never close this parenthesis. Well, the error wasn't that I never closed that parenthesis, it's just I put the wrong one. I had an open when I wanted an open close, right? So pretty good. But then we saw that one with def that was perhaps a little misleading, because it looked like it was saying the issue is with the B, but it wasn't really. It was just around there. Because of the context, it's kind of difficult to know. And you might find, and of course I can't think of one right now, which is annoying. You might find sometimes it'll be like there's an error on line 99. and you're looking at line 99, there's no error on line 99. There's nothing wrong. But sometimes the error will actually be like at the end of line 98. So you always have to look also around where it's saying the error is. Because the error that it found might be related to an issue that actually existed a little bit before it, but it only really discovered the issue like there.
I mean, with your function being big wrong, that would produce an error. That would, like it would say the error's on line 5.
Yeah, I suppose you're right. Yeah, Borkin. Well, right.
Yeah, because Python was great.
Whoop, not that. Yeah. It's not defined. You're right. So the error was that, you're right, that's a good point. The error was actually somewhere else. Although, depending on like, well, what was spelt wrong? Was it the call or the definition? Yeah. But you are right. That was kind of one where it was a little, there was some distance between where it said the issue was and where the issue kind of was for our needs. Good point, though. Good point. Now we have type errors. Now these ones in Python aren't necessarily going to tell you that there's a problem. It's going to be like, great, you told me what to do, I'm going to do it. So if I have, it's an integer, float, mixing types in this expression, and no big deal, right? So Python's pretty good with types. If I add these together, I'm going to get 10.5, right? It's fine. But Python can only do so much, right? Like if I did something like this, 99 plus bottles of beer on the wall, I'm going to get a type error. And this is a type error where I'm trying to use an operator in a way that is not defined how to work. I'm saying add this number to a string, and Python goes, what is that? And every once in a while you get someone that asks, well, why can't it add a number to a string? And I go like, okay, what's 99 plus hello? And you go like, well, yeah, how do you add a number and a string together? That doesn't really make sense. You can come up with a way to add it together. Well, I think what it should do is, okay, that's what you think, but... So this is an issue because I'm trying to add an integer to a string. Well, how do I resolve it? Well, I would have to turn this 99 into a string, and then I can add strings together to concatenate them. That's fine. Or I could use an F string or something that kind of manages the type issues for me. So sometimes Python, it's good with strings, it's happy, or it's good with numbers, it's happy, no issue with the types here. Sometimes it's good, and it'll tell you like, you know, I can't add these types together, and it'll give you an error message, and it tells you can't add an int in a string, and you go, what? And you go like, oh yeah, that's an int. I can't add those things. But sometimes I get in situations, like I've shown you before, here's a function called inconsistent. It takes two values, and it returns their sum. If I give it the values 1 and 1, I get 2 back. If I give it the values, the strings 1 and 1, I get back 11. You might think, well, no big deal, but you know, if you're not careful with like let's say you're inputting data with the input function, whenever you input something, it's always a string. And if this is a very important calculation, and it needs the sum of these two numbers, and you get back 11 when it should be 2, you're going to be wrong. This is controlling the nuclear control rod of your spaceship. And it's doing your division wrong because it calculated the sum of two things the wrong way. We're in big trouble. And Python is happy to do this for you. Here, it's 11. This is what you wanted. But you used the wrong type. Now, in other programming languages, like Java, which we'll be using next semester, this wouldn't really be possible. Java wouldn't allow you to make these types of mistakes, which is awesome. It's great when the language has stuff like that built into it. Yeah, okay, so it may seem obvious that one should not call the function with the wrong argument types, but also consider reading input from the user. How many times have you accidentally not converted your input to an integer when it should have been an integer because it was a string and yada yada? Any questions so far? Is that a question back there or just a, no? Cool. All right, logic errors, on the other hand, well, this is where the trouble happens. These are often errors where you hit run, you get an answer, looks good, but something went wrong. You don't know what went wrong, and sometimes you don't even know something went wrong. You think you got the right answer. You print out 11, you're like, my function gave me back 11. That's great. So that's kind of a logic error, I suppose. But a function where everything computed, the program didn't crash, and it gave you an answer, but ultimately it was wrong. And sometimes these are really sneaky. You might not even notice it's wrong. So these are where the difficulty comes when you're debugging. Everything may seem to be working, but in the end, something's off. Sometimes the errors may be obvious, like an infinite loop. Sometimes they're really sneaky. They kind of come up in edge cases where like 99.9% of the time, everything's fine. But it didn't work. Only one time in my undergrad degree, only once did I ever submit an assignment that I knew wasn't perfect. And it was in this, I was making something called like a B plus tree, which I would never make a student do because it was so terrible. But I mean, hey, my colleagues might, so don't get too excited. A B plus tree, and it worked. And the whole point of the B plus tree is it can store massive amounts of data effectively. And everything worked until finally the teacher gave us like a data file with like 1 billion entries into it, and we had to load it in. And it would like work like up until like 70% through the file, and then something would go wrong. And I could never figure it out. And I knew it was wrong. It worked on every other example, but as soon as there was something in that one instance of the problem where like something went wrong, and I could never found the issue. I would never go back looking for that issue because the code was god awful, and I would never be able to make sense of what the hell I was writing at the time. You're better programmers than I was. Don't you? You have a much better teacher than I had. So, see the joke there. No, the joke, to be clear, the joke is, remember, I'm not your teacher, you're your teacher, and I was my teacher. So there's actually layers to that anyways. So only once, and it was an edge case. It was clearly an edge case. It was a sneaky one. I don't know what was wrong with it, but something was wrong. Yeah.
You think you could do the right thing now?
Could I do it now? I'm certain I could because of how, and the reason why I'm pretty damn confident is I'm certain that I would never have been able, the way I would write the code now, the way I tell you how to write your code is a way that is so defensive that that issue would never come up in the first place to need to be solved, if that makes sense. There honestly is almost an argument to let students be bad programmers so they have more experience debugging shitty code, because that's a really important skill to learn. But I think it's probably better to just write good code in the first place. So if I wrote it now, I probably wouldn't recreate the same bug. And if I did, I'm certain with my experience now I'd be able to find it. But I don't want to like jinx it because I'd make a pretty big fool of myself. Yeah. Anyways. So there are a few strategies for distilling these bugs. A few accessible strategies for debugging are discussed below. Most people develop their own strategies. I used to call these coping mechanisms, but my colleagues were like, come on, don't be that. But I still think it's funny. But like everything else, you're going to get debugging. You're going to get better at it with more practice. And oh boy, you're going to get a lot of practice. Has anyone in here, on a scale from 1 to 10, how many bugs have you had? Is the number over 7? On a scale from 1 to 10 on like the volume. Yeah, and if it's not over 7, it's sure shit gonna be. It's only gonna get worse. And I mean that in the best way possible. All right, yeah. Any questions before we wrap up? All right, I'll see y'all, some of you tomorrow and the rest of you Friday.